Okay, well, it is now 10 after, so let's go ahead and get started. Welcome back to MAT1841. So last time we talked a lot about conductance and epsilon mixing time, and we had a really long and involved proof, which we didn't quite finish, and I got sort of rushed on nearly end. So the first thing we're going to do today is I'm going to add in a minor correction. So it's just a slight constant that I forgot about last time in the proof, as well as finish proving the lemma. Then we're going to talk about convergence of random walks on grids, since those are a very nice shape. And then we're going to go back to Markov Chain Monte Carlo and use our newfound knowledge of mixing times to construct good Markov chains that mix fast for sampling particular probability distributions. We're going to see one application of that. So we're going to see how we can compute high dimensional volumes using MCMC. And lastly, we're going to talk briefly about PageRank, which is another widely used application of Markov chains. And that's also why I'm wearing my Google t-shirt today, because that was one of the things that made them, well, made them what they were to begin with. So let's go ahead and get started. The first thing I'm going to do is I'm actually going to just work on last week's notes instead of working on a new page. And I'll upload the updated version, of course. And I just wanted to make a couple of small corrections. Someone asked this in Piazza, and I realized that I had forgotten the constant. So the correction is that I'm going to write down two facts. They're both really useful. So one fact is that log of one, let's see, this is correction or addition or whatever. Log of 1 plus x is always less than or equal to x. Okay, so this is well known. Another useful fact is that log of 1 plus x is greater than or equal to x over 2 for x in the range from 0 to 2. Okay, so one of the issues was that someone noted that my inequality sign went the wrong direction. And that was down, looks like down here. So someone was like, wait a moment, if log of 1 plus x is less than or equal to x, how does this inequality make sense? And the answer to it is that it doesn't actually. But what we can do instead is we can replace this 4 with an 8, and then this is true. Okay, because we're in this regime. Okay, and of course, then that means we need to change this one here as well, and so on. Okay, and that of course means that when we actually do, actually we have a little bit of time, so let's actually follow through the steps of this derivation as well, just as a reminder of what we were doing. So just a reminder, the basic premise was that we wanted to bound the epsilon mixing time of a random walk on an undirected graph via the conductance, which we defined as basically the probability that you're going to move from the smaller side of a partition to the larger side in one step. Okay? Any questions before we get started? So let's actually work through this. So we have r times 8 over t phi epsilon. So that's going to be equal to, well, 8 over epsilon phi times log of 1 over pi 1 plus 2 times 8 over phi epsilon. And then we substitute in for t. And so that's going to give us pi squared epsilon cubed over c log of 1 over pi min. And well, these things we can cancel out a bunch of these things, and you end up with 8 over epsilon phi times another factor of 8 over epsilon phi times phi squared epsilon cubed over c times log of 1 over pi 1 and log of 1 over pi min. But of course, we can relate those two to each other since pi min is less than or equal to pi 1. And so this entire thing is less than or equal to 1. Plus 16 over phi epsilon times phi squared epsilon cubed c log of 1 over pi min. And this entire thing, when you work through all this is less than or equal to 64 over c times epsilon plus 16 phi epsilon squared over c log of 1 over pi min, which is less than epsilon for some c because we know that phi is less than 1 and log of 1 over pi min is greater than 1. Okay, so that was the logic that I was rushed through last time. And this time, we're going to actually prove this technical lemma. So what was the lemma we used? We had some bound on the on the sizes of these rectangles, right? So we had some bound on the sizes of the rectangles that we had there, and that was how we proved our main theorem. But now, of course, we need to prove how much probability there is in those boxes. And the way we're going to do this is, let me write this down, proof of lemma, is we're going to use two different ways of computing probability flow. So we know that there's probability that's flowing from a heavy states to our light states. Remember, the heavy states are just the ones that have more mass than the stationary distribution, and the light states are just the ones that have less mass than the stationary distribution. And clearly, you need your mass from the heavy states to your light states. And we're going to compute this flow in two different ways, and then that's going to give us a useful bound. So let's first start by considering a starting probability, A, and we know that A minus AP is the net loss in probability for each state after a step. Okay, so this is basically the delta, like how much are you changing from one step to the next? Is, of course, well, you start with your probability distribution, and then you hit it with P with your Markovian transition matrix on the right, subtract away, and that gets you exactly what we care about. So now let's consider, and of course we use the standard A is actually, in this case, the average over the time from 0 to T minus 1. 3 parentheses. Okay, so that's what we're going to start with. And now we're going to consider a group of nodes. Consider a group. Let's call this GS. Is going to be K plus 1, all the way through L, where we know that K is less than I naught. What was I naught again? I naught was the first light state, right? So remember, we ordered everything so that you go from the heavy states to the light states. And I naught is the first light state. And then what we do is then we let A be equal to the set from 1 through K. So then the net loss for A in one step at time T is going to be the sum from I equal 1 to K of AI minus API. So I'm using this notation to denote the ith coordinate within that vector, which is less than or equal to 2 over T. And this is, of course, because by the convergence proof. So by convergence proof, since A of T P minus A, wait, what did I do wrong here? I just did something wrong. Oh, yeah, that's what I did. So let's ignore the of T's. A minus A P is equal to 1 over T times P of T minus P of 0. Okay, so this is one way of measuring the amount of loss of the probability mass from the states in the set A from 1 through K. Okay. The next thing we're going to do is we're going to take, we know that for any I, actually, let me write this out. So now let's consider another way. Consider another way to measure probability loss. And this time we're going to do it a different way. Instead of just measuring this, oh, well, as you evolve your Markov chain, this is how much you lose. Well, we also have this other idea of flows from one set to its complement set, right? So like flows from A to A complement, like that's how we define conductance. And so we can make use of that sort of framing as well. So we're going to take the difference of flows from A to A bar and A bar to A. So note that for any I less than J, we know that the net flow, I'm going to use this notation, from I to J is, well, obviously the flow from I to J minus the flow from J to I. And we can compute that explicitly. So that's going to be AI times Pij. So that's the AI is, of course, how much mass is currently on I, and then Pij is how much of that mass is flowing over to J, minus Aj times Pji, which is exactly the complement, which is when we write this out, remember that we defined our VIs in such a way that this is pi I Pij Vi minus pi j Pji Vj. Okay? And now that is equal to, of course, just pi j Pji, because pi is our stationary distribution. Do you mind keeping your mask on? Yeah. Oh, no, yeah, that's fine. Sorry. No, go ahead and take a drink. Yeah. But yeah, so Pji times Vi minus Vj, which is greater or equal to 0. Why is that greater than or equal to 0? Yes, exactly. So originally we re-indexed, remember? So we re-indexed everything from heaviest to lightest. And so Vi is heavier than Vj, or I is heavier than J, and so Vi is greater than Vj. And and of course, these two things are equal because this is a stationary distribution. So what does this tell us? So for any two nodes, there is non-negative flow from heavier to lighter. From heavier to lighter. Yeah, okay. So now let's continue and note that since L is greater than or equal to K, remember we defined this thing up here. L is greater than or equal to K, and therefore flow from A to the set K plus 1, K plus 2. Actually, I think I might have meant to start this at K plus 1. Well, we'll see if that works out in a moment. So the flow from A to K plus 1, K plus 2 through L minus flow from K plus 1 through L to A is non-negative. And now we're going to be doing a lot of playing with indices. And so please, if you see me doing a wrong index, catch me because it gets quite complicated. So for I less than or equal to K, we have that J is greater, and for J greater than or equal to L, remember our K and L were, L is greater than K. We know, and we know that Vi is greater than or equal to Vj. Okay, so that's just by our indexing. And we know that Vj is less than or equal to VL plus 1. So therefore, the net loss from A is at least the sum for all nodes I less than or equal to K and J greater than L, pi j, Pij, Vi minus Vj, which is greater than or equal to Vk minus VL plus 1 times the sum from I less than or equal to K of J and J greater than L, pi j Pji. Okay, and so we're making extensive use of our sorry. We're making extensive use of our indexing here. Okay, plus we know from lat that Vk minus VL plus 1 times the sum from I less than or equal to K, J greater than L, pi j Pji. What do we know about that? So remember, the whole premise of this lemma is we're computing probability flows two different ways. This is one way of computing the probability flow. Did we compute the probability flow a different way earlier? Yeah, so we know that this is also less than or equal to 2t by our other computation. Okay, so now we have a bound on listing by using both our computations separately. And so now if we just continue on pushing around some symbols, for sum from I equal 1 to k, and the sum from j equal k plus 1 to L. I'm just rewriting stuff here. Pi j p j I. Well, we know listing is less than or equal to the sum from j equal k plus 1 to L of pi j, which is then less than or equal to epsilon phi pi of a over 4. And this is by the definition of L. Why is this by the definition of L? Because way back when we came up with the mechanism for deciding how much, where to do each of these G sub S groups, the way we define them is we define them as the maximum number such that we don't have too much mass in them. Remember? So back here where we were doing list definition. Okay, and now we know by the definition of phi and using the fact that minimum of pi of a and pi of a bar is greater than or equal than epsilon over 2 pi of a. We know that the sum for I less than or equal to k less than j, pi j p j I is greater than or equal to phi times the minimum pi of a times and pi of a bar, which is greater than or equal to epsilon phi over gamma k over 2. Okay, here note that we've made use of our definitions of conductance. So where was that? That was all the way back here. So remember we had this definition here. So we're making use of our definition of conductance and then pushing around some of the things between numerators and denominators. Okay, so we're almost done now. So just bear with me for just a little bit longer. Then we know that the sum from I less than or equal to k, j greater than L, pi j p j I. Well, what is this? Well, if you think about it, we have a bunch of nodes, right? And we have some node k there and some node j here. And what we're doing here is we're measuring the amount of mass we're pushing from here to here, right? That is what the sum is saying. We're pushing how much mass is being pushed from nodes smaller than k to nodes bigger than j. Well, this is of course just equal to the sum for let's see, I less than or equal to k less than j, pi j p I j. Wait, did I mean p I j? I think I might have meant p j I. P j I minus the sum from I less than or equal to k less than j less than or equal to L, pi j p j I. What are those? Well, in each case, we're pushing mass from some place to a different place, right? So here, what we're doing is we have our k and we have our L, and we're starting here, and this is how much mass we're pushing over to this entire region. Okay, and this is just mass you're pushing from KL from here to here. Okay, so this is just where that inequality comes from. And once we have that, we know that thing is going to be greater than or equal to epsilon by gamma k over 2, which then implies that bk minus bl plus 1 is less than or equal to 8 over t epsilon by gamma k. Note that for this assumption, we assume that k is not equal to I naught. It's the same sort of argument, but slightly easier for k is equal to I naught. Okay, and that was a really ugly sort of really technical proof. There's a slightly more expanded version in the book if that's still not like if you need to work through all the indices carefully. But basically the idea is we were able to compute the same quantity 2 different ways and then use both of the different ways combined together to bound the amount of mass. And that of course completes the proof of this theorem, which the whole point of this all is just basically to say that if you know the normalized conductance of a Markov chain, then you have both a lower and upper bound on how quickly things can mix. It's not necessarily a tight bound. So it turns out that there will be cases where this is very not tight, but at least this gives you a bound that so long as the conductance is high, your mixing time is not too slow. Any questions about that before we move on to other parts of the lecture? Okay, so let's actually get started on today's material. So we just did minor corrections to the proof, finished proving the lemma. So now let's apply it. So now we're just going to treat that entire thing as a black box. And let's talk about random walks on 2D grids, or on grids in general. And we want to ask, how quickly does the probability distribution converge to the stationary distribution? So let's do this on a very, very simple example. So this is a random walk on 2D grid. And I'm going to draw a grid to make life easy for us. So let's make this a 4x4 grid, but it's really going to be an n by n grid. And I'm going to connect every single one of these with each other. Oh, I should just draw lines. That's an easier way of drawing a grid than drawing them one by one. Okay, so now if I gave you this grid, and you could compute the stationary distribution for random walk around it, right? But of course, it wouldn't be exactly the same everywhere because on the edges, the degree of those nodes is slightly smaller, right? So for the sake of making life easy for us, I'm going to add a couple new self loops. So I'm going to add a self loop here because I'm missing an edge, right? So I'm going to add an extra edge there, and I'm going to add another edge there, and so on. And note that on this corner one, I have to add 2 edges, basically to ensure that the degree of every single node is the same. So what happens if the degree of every single node is the same as far as the standard random walk on the graph is concerned? What can you tell me about the stationary distribution? Yes, exactly. So we have now constructed a grid where the stationary distribution is uniform. Note that Pij is going to be equal to 1/4 if I and j are adjacent, because it's a standard random walk. I and j are adjacent. Adjacent. And we know that pi I is going to be equal to 1/n² is the stationary distribution. Now, unfortunately, in practice, you're usually not going to have things that are quite this nice, but making everything this nice makes it a lot easier for us to actually compute the conductance. Because one of the trickiest parts of computing the conductance is, of course, the fact that you need to look at every single one of the subsets, right? Luckily, in this case, all the subsets are pretty similar, and you can sort of class the subsets together, and this allows us to actually compute bounds on the conductance. Okay, so now let's start by consider any subset S where of size less than or equal to n²/2. Okay, so remember when we were talking about conductance, it is there's a minimum in there. So you're always going from the smaller of the subsets to the bigger one in terms of what you're measuring. And so we're just going to assume that we're going to consider all subsets that are at least smaller of the 2 halves. And by that, if you're worried about the conductance starting from a bigger subset, well, it doesn't really matter because of definition. Okay, so now what are the different cases? So I'm going to make a claim. So if S is at least n²/4, then at least n edges leave S. Why is this? Well, what are the different things that can happen? Well, one of the things is if you had a grid, S could be just a corner of this grid. So if it's n²/4, you could fill up an entire quarter of the grid. But in that case, note that there are n/2 edges that come out there and another n/2 edges that come out here. So even in that case, you're fine. What happens if it's not quite like this? So what happens if you're not quite exactly a perfect square? Well, when that happens, you still get the same sort of behavior. So if you happen to have an entire column and some other stuff like there, well, then you have all these edges here. So there's still n/2 edges that go off onto the rest of it. And so because n is because the number of nodes is less than or equal to n squared over 4, it turns out that however you arrange things, you're going to have n edges to the rest of the graph. And you can stare at that a little bit longer to convince yourself, but this is basically the logic, is that however you arrange your nodes as you pick them. Obviously, you need to put them in a block, because if you don't put them in the block, then there are lots more edges that go out of the subset. So and then you can think, well, what are the different ways of having a contiguous block of nodes, such that you have the least amount of edges going off onto the other half? Well, one way of doing that is to ensure that you're in a corner. Because if you're in the middle, you're just going to have more edges. So you have to be in a corner on a side, but you can't take up an entire side, because if you take up an entire side, well, then there aren't enough edges for you to take up 2 entire sides, and therefore there will be at least n edges. If you don't take up an entire side and you try to make everything as compact as possible, your square is still at least size n over 2 by n over 2. Yeah. So anyway. So we have the logic, at least n edges leave it. But then if at least n edges leave it, then that allows us to put a bound on the conductance, right? So thus we know that phi of s is going to be equal to the sum from I in s, because s is the smaller of the two. So instead of using the min formulation, we can use the formulation where we know that s is the smaller of the two. So pi I over pi of s times the sum from the sum over j in s bar of pij. But we have made life really easy for ourselves by picking a really nice uniform distribution. And so we know that this is just equal to 1 over the size of s times the sum over I in s and j in s bar of pij. And so this, and now what exactly is the sum from I in s to j in s bar of pij? Well, for each edge between I and j, if it exists, then you have a 1/4 probability, right? If it doesn't exist, then you don't have a 1/4 probability. But now, how many edges are there from from the set S to the set S bar? At least n. So this means we have at least n over 4 times S bar. Sorry, the absolute value of S, which is greater than or equal to 1 over 2n, which is omega of 1 over n. Okay, so that's the case where we have at least n squared over 4, but less than n squared over 2 nodes. So let's consider another case. So what happens if we have very, very few nodes in here? If s is less than n squared over 4? Well, then there are two cases. So case 1, let me write that as case 1. Well, let's say that case 1 is you have at least a column. So at least a column or row. Well, if that happens, well, then you get exactly this situation, and this same logic holds. Okay, so from that logic, we know that we don't have to worry about the set S when it's less than n squared over 4, because then there are at least n edges that leave it, and we can just use the logic of the previous case. But let's say case 2. Well, if it's not at least a column or a row, then it ought to be some kind of rectangular shape in a corner. It doesn't have to be a rectangle necessarily, but it's stuck in the corner somehow. And so if it's stuck in the corner somehow, well, then if it's stuck in the corner, but it's of course a small square of some kind, well, we know that there are at least, so this case, at least 2 times the square root of S points adjacent to S, right? Because you want to compactify everything, and the most you can do is, roughly speaking, 2 times the square root of S, like edges on the 2 sides. So here, this is square root of S, and here, this is the square root of S. So once we do that, then we do the same kind of argument again. Well, what's phi of S? Well, that's the sum from I in S of pi I over pi of S, which is just going to be 1 over the number of nodes in S, times the sum from J in S bar of Pij. That's, of course, just 1 over the absolute value of the number of elements in S times this double sum. But this double sum is, of course, again, just counting edges divided by 4. And we know how many edges, we know how many, there are at least 2 square root of the cardinality of S edges. And so this is equal to 2 times the square root of cardinality of S divided by 4 times cardinality of S, which is equal to 1/2 times 1 divided by the square root of cardinality of S, which is greater than or equal to 1/2 times 2 over n, which is equal to 1 over n. And 1 over n is clearly omega of 1 over n. So combined, this means that phi of S is clearly omega of 1 over n, which implies that the epsilon mixing time, when you plug all this back in, is equal to O of n squared log n over epsilon cubed. Is this good? Would you be proud of this result? Like, is this useful if we want fast mixing? Yeah, that's a really good point, right? How many nodes do we have in this graph? We have n squared nodes. And what I'm saying is that in n squared log n time divided by epsilon cubed, I get good mixing. So this actually, so it turns out a 2D grid does mix quickly, but this proof here does not actually tell you that it mixes quickly compared to the cover time. Or I mean, mixes quickly compared to just the amount of time you need to take to explore all the nodes of the graph. So this isn't actually that good, since we still explore nearly all the points, right? So or I mean, you don't necessarily explore all the points, but you explore most of the points. And so if like the number of points were exponential, then that would take exponential time. So this argument actually doesn't help you too much with a 2D grid, but you can generalize this argument for higher dimensional grids, and there it actually does help. So higher dimensional grids. So basically using the same kind of logic of just like bounding the number of edges that leave. If you have a high dimensional grid that is an n by n by n all by n, so let's say there are d of these. So we're in the d-dimensional grid, d-dimensional lattice with the same self-loop at boundaries construction. So if you do that, well, you again get the stationary distribution. Pi I is just equal to 1 over n to the d, because every node has the same degree. Same degree. And so I'm not going to work through all different cases because it gets sort of ugly, but using similar reasoning as above, it turns out that the conductance is going to be equal to omega of 1 over dn. Okay, so you do have some scaling by dimension, which is what you'd expect, but it turns out when you plug that in, what you get is that the epsilon mixing time is O of d cubed n squared log n over epsilon cubed. And note that now this actually is good because this is a much smaller polynomial than n to the d. So this is poly in n and d rather than exponential. And this is, of course, much smaller than the cover time. For cover time, just the time it takes to explore everything, omega of n to the d. Okay, so conductance, we've developed a particular tool for like figuring out the mixing time. It turns out this tool isn't necessarily the strongest in all cases. So for the 2D grid, convergence is actually a lot quicker than the n squared log n, but conductance isn't powerful enough for us to prove that because of all the inequalities we had. So it's not a tight bound. But this is powerful enough to show that in the higher dimensional grid, you do converge much faster than you would than exploring all the different nodes. And that is quite important because we're going to be showing, because we're mostly working in high dimensions here, right? Okay. So basically what we've just shown is that high dimensional grids, high dimensional lattices, if you have a random walker on there with uniform probabilities everywhere, do actually converge quickly. Now, the high dimensional grids you're going to be working with momentarily aren't going to be perfectly uniform, but this is still just trying to give you a flavor of why those high dimensional grids do work, and they do actually converge quickly in practice, even though proving it for any particular probability distribution can get slightly thorny. So let's take a step back and talk about MCMC again. So what was the point of MCMC? The point of MCMC was that we could sample a probability distribution in some high dimensional context, right? Quickly, if your Markov chain mixed quickly. So now, what are things we can do? Of course, we didn't actually give any construction for what Markov chain we wanted to use to sample a particular probability distribution. So that's what we're going to do now. We're going to give you two different constructions for these Markov chains that will match a particular probability distribution you're trying to sample. So the first one is called Metropolis-Hasting. And well, let pi be the probability distribution we want to sample. So this is our desired stationary distribution. Desired stationary distribution. On the states b is equal to 1, 2 through n. Well, the first question is, if I just gave you the assignment to construct a probability distribution like this, what would be things that you could consider doing? If I told you, don't worry about convergence time, I just want you to construct some Markov chain that has this probability distribution on its states. So what stationary distributions do you guys know? You guys don't know that many of them. How did we get the stationary distributions of these things here? Yeah, so why were we adding those edges? We were adding those edges because those edges allowed us to make all degrees the same. Because the stationary distribution of the standard random walk on an undirected graph is precisely the proportional to the degree of all the nodes. So if I just ask you to construct some Markov chain that had this stationary distribution, all you would have to do is ensure that it's a connected graph and this is the correct degree of all the nodes. So that would work. And in fact, if you used weighted graphs, it makes it even easier because then you don't need to like balance out the numbers of edges. But yeah, so that would work, and then you would end up with the desired stationary distribution. You could even just put it in one big long chain. You have one big long chain and have enough self loops that things stay in place, right? So you can think of it as, oh, well, I'm just going to create a chain of things all with probability 1 to move to each other, and then I'm going to add a self loop of sufficient weight that all the probability distributions work out. When you do that, it of course takes forever to converge to the stationary distribution because you need to walk all the way down the road. So that's not a particularly clever way of doing it, but that gets at the sort of sense of how we want to construct these Markov chains, which is all we need for the degree distribution to be correct on undirected graph, and that'll give us the right stationary distribution. We're going to do something slightly fancier, which is we're going to start with that idea, start with an undirected graph, and then define a slightly different random walk on it. So not quite the standard random walk. So what we're going to do is we're going to let G be equal to VE, be any connected undirected graph with max degree R. Okay, where degree is just the number of undirected edges that include the node. Okay, and undirected here just means that if the edge from I to J is there, and so is the edge from J to I, and they have the same weight. Okay, so we have any connected undirected graph. So at a node I, we're going to choose each adjacent node with probability 1 over R. And you're going to have probability 1 minus degree I over R of choosing none. Okay, and so in some sense, the probability of choosing none is basically somehow something like a probability of a self loop. You're just equalizing all these probabilities. But if you have adjacent nodes, since we know the max degree of this graph is going to be R. I haven't told you what graph it's going to be, but the max degree is R. And so clearly you can say, I'm going to choose an adjacent node with probability 1 over R. But now the trick here is instead with the standard random walk, you just be like, okay, well now I'm going to walk over to the other node, right? But that's not quite what we want here, because we're not trying to construct a uniform distribution. We're trying to construct a particular distribution. So the next thing is, instead of immediately walking over to the node we've chosen, we're going to walk over only with some probability. So what are we going to do? So if an adjacent node is chosen, if the pi j, if node j, let's call this j, node j is chosen, if pi j is greater than or equal to pi I, go to j. So if the amount of mass you want on node j is greater than the amount on node I, well then always walk over. But on the other hand, if pi j is less than pi I, we go to j with probability proportional to the amount of masses between the two. Okay, so this is basically ensuring that the net probability flow goes in the correct amount over to the nodes with higher weight. And otherwise, stay in place. To write this a little bit more formally, Pij is equal to 0 if edge ij does not exist and I is not equal to j, and ij is equal to 1 over, oh, sorry, I'm working offline, is equal to 1 over r times the minimum of 1 and pi j pi I. If there exists some I and j, if that edge exists and j, I is not equal to j. And the pii, so the probability of staying in place, is just 1 minus, well, all the other probabilities. Plus, what we get is if there does not exist an edge, ij, then pi I pij is equal to 0 is equal to pi j pji. Okay, so that's symmetric, so that's good. On the other hand, if there does exist an edge between the two, then we know that pi I pij is going to be equal to pi I over r times the minimum of 1 and pi j over pi I, which is equal to 1 over r times minimum of pi I pi j. And of course, that's equal symmetrically to pi j pji. And therefore, because the net flow from I to j is the same as the net flow from j to I, that means that this actually, that pi, so this implies that pi is the stationary distribution. This is the stationary distribution of the Markov chain. Note that this is for any connected graph, but of course the shape of the graph will affect the mixing time. And so there are ways of constructing graphs such that the mixing time is relatively low. So for example, things like expander graphs tend to have low mixing time if those are concepts you're familiar from combinatorics. But this doesn't actually say what graph to choose. It just says construct any graph, and this will work. But if you choose a better graph, it'll work faster. Any questions about that? Okay, so that's one way of doing it. I'm also going to give you one other commonly used way of doing MCMC, which some of you may have heard of, especially if you're from a more physicsy background. This is called Gibbs sampling. Have people heard of Gibbs sampling before? Okay, a little bit here and there. But so Gibbs sampling is slightly different. So I'm actually going to give you effectively an explicit graph of connections between things. So what we're going to do is we're going to let P, I'm going to call the target distribution something slightly different, be the target distribution, where our states are some multi-dimensional space. where x is equal to x1 through xd. So you're sampling in some d-dimensional space. Of course, we've mostly been talking about in the discrete setting. There are natural generalizations of Gibbs sampling to the continuous setting as well. So you're operating in some multidimensional space, and your states are all different points in this multidimensional space. Well, you can imagine constructing a graph. G is equal to VE, B, and an undirected graph. The graph where B is the set of all states of X. And we say that X and Y, two different points, have an edge between them if and only if the 2 points differ in at most one coordinate. So here I'm using the zero norm. Basically, I'm asking how many points do the two states differ in? And so I'm saying I'm going to connect two states if you only have to change one of your d coordinates in order to get to that other state. Okay, so let me write that down, i.e. Two states differ in only one coordinate. Two states are connected by an edge if they differ in only one coordinate. So what does that mean? That means that whenever you're walking along your Markov chain, you can only ever change one of your coordinates at a time. And so this is, so at each step of our walk, we choose one coordinate to update and keep all others fixed. Keep all others fixed. So basically, you can think of it as each state is connected to a bunch of other states, depending on which of your coordinates you're changing, right? And so you're going to equalize the amount of probability mass of changing any one of your coordinates. So you're going to, and effectively, you're going to randomly choose one coordinate to update. In practice, often you don't actually choose that coordinate randomly, you choose it sequentially. But for our purposes, it's easier if we think about it in terms of there's choosing a coordinate randomly to update. You keep all others fixed. So you can do this randomly or sequentially. And well, so if we suppose that these two states differ in only one coordinate, without loss of generality, we can assume it's the first coordinates. Suppose they differ in the first coordinate. Then what we're going to do is we're going to set Pxy is going to be equal to 1 over d times the probability of y1 given all your other coordinates. So you're going to hold all your other coordinates constant, and you're just going to sample from whatever probability distribution there is over this one coordinate. Now, of course, that might be tricky in its own way, but you're basically assuming that it's easier to sample one-dimensional distributions than it is to sample multi-dimensional distributions. So that's basically what Gibbs sampling is. So you randomly choose your coordinate based on all these other coordinates, and when you compute this out, you'll find that because of the way we've constructed this, the probability of being state x times the probability of going from x to y is equal to the probability in state x divided by d times p y1 given x2 through xd. But of course, x2 through xd are the same as y2 through yd because they only differ in the first coordinate. When you expand this out, you get px1 through xd and py1 through yd divided by d times px2 through xd. So just the standard application of conditional probability. And when you can combine this together the other way, and this ends up being probability of y times p, being y times p transition probability from y to x. Is there a question in the chat? Okay, so this is basically Gibbs sampling, which is commonly used in practice when you're trying to sample from some multidimensional distribution. Well, if you can sample from any single one of the coordinates at a time, well, then this allows you to then sample the entire distribution. And if you look at the connectivity of lists, this says the sort of lattice-like connectivity, because every state is connected to all the other states where it differs by only one node. And so this also mixes relatively quickly. I am out of time, and I have so much more that I wanted to cover today. I guess that means that we are not going to get to PageRank today, which is a little bit sad because I even wore my Google t-shirt. But okay, so next time we will talk about estimating volumes using MCMC, since that was a sort of motivation for this. And I'll briefly mention PageRank, and that will complete our sort of section on Markov chains. And then we'll talk. One of the things that we'll be doing in the next couple of days is I'm going to give you a brief whirlwind overview, probably via PowerPoint or something, of all the various other topics we're going to be covering in this class. And then once we do that, I'm going to, because I want you to start thinking about your projects relatively soon. So you guys haven't seen all the various material in this class. I'm going to give you a brief overview of that, and then you can start thinking about what kind of project you'd be interested in doing. I will also think about some projects that might be appropriate, but just start giving that a little bit of thought. But yeah, so we're not quite done with Markov chains. That'll still be a little bit of work tomorrow, but then we'll continue moving on with some other materials. Thank you all very much, and I will see you tomorrow.